Hello viewers, welcome back to the channel Sampurna Adhyan. In this particular video, I am going to talk about that how to simulate the resistive firing circuit for the SCR triggering. As a next part of this, I will also make a video based on that how to simulate the resistive and capacitive firing circuit for the SCR triggering that you can see in my next part of the video. And I will also upload some other PSpice related projects, so you can please visit the channel page and the playlist also, and you can please subscribe the channel, and you can press bell icon to get the further notification on the latest uploads based on the PSpice projects and other technical videos. So now let's start with the resistive firing circuit for the SCR triggering. Here, this circuit I am going to consider for the simulation, and I would like to tell few important things related to this particular circuit. This is our dedicated SCR. Its terminal are anode, cathode, gate, and basically we have two type of circuits in this SCR. One is power circuit, which is actually concerned with the applied source and load and SCR, and other one is a control circuit, which is actually responsible to provide the triggering pulses between the gate and cathode. So here we can see that the outer loop is nothing but working as a power circuit, because here the source AC voltage source is connected. It can be step down supply as per the rating of the SCR also, and secondly the load is also connected in series with the SCR. Once the SCR will conduct, it will become in the series with the voltage source, and the major current will flow like this. That's why it is a power circuit. Now as far as concerned to the control circuit, this particular resistive division based circuit is utilized here, in which diode is also connected, which provides the unidirectional current flow towards the gate. And also these resistance are very important, and I will tell you that what is the relevance of connecting these resistances. These resistances are actually responsible to provide the certain control of the gate current, as well as the gate to cathode voltage applied to the SCR. And this particular part of the circuit, which is itself connected across the voltage supply, is also known as a control circuit for the SCR. Also, one of the important thing with the resistive firing circuit is that it can provide the firing angle control between 0 to 90 degree only. And if you refer your textbooks or the other study materials, you will find that how it is actually limited to the 0 to 90 degree. Actually, ideally we cannot get the 0 degree also. We practically get only 2 to 4 degree to 90 degree operation. Also, we can see that here two resistances R1 R2 is connected in the series, where R2 is a variable resistance and R1 is a fixed resistance. Why we have connected the R1 when we have connected the R2 variable resistance to control the triggering? We can consider that sometimes if the R2 value is 0, then some resistance has to be there to stabilize the gate current flow through the SCR. That's why the R1 is an extra current is extra resistor is connected in this in series with this variable resistance. Also, there is a one more resistance R is connected between the gate to cathode to ensure that whatever be the applied voltage across the gate to cathode of the SCR, it should not go beyond the maximum rating of the SCR. Whatever be the SCR you will use, its data sheet used to be there, and according to that you can decide that what is my maximum gate current it can be here, and what is the maximum gate to cathode voltage it can be here. Based on this particular circuit configuration, we have the parameter derivation also, that what is the value of R1. Like your gate current should not go beyond the maximum gate current at any time when the R2 is 0. So you can consider this IGM, that means maximum gate current is here, and your actually applied the gate current should be always less than or equal to this. So what is the your IG in this case? If we consider the maximum supply maximum of the supply voltage, that means at that particular moment supply voltage will be maximum, so the current will be maximum. So you will get this Vm upon R1 relation, because it only going to decide that what is the maximum gate current going to flow here. So if we consider the R2 is 0, So this should be always less than the maximum gate current of the SCR as per the data sheet, and this will give you the value of R1. That is, R1 should be always less than or equal to Vm by Igm. That means maximum of the supply voltage upon maximum gate current SCR, whatever with the SCR you are using can withstand. Now the next important thing, what should be the value of R? This we can decide by the help of that what is my maximum rating of the gate to cathode voltage for the SCR we used. So we can consider that if we consider R2 again 0, then this resistance, because once the diode is forward bias here, it will become a simple potential divider circuit. So we can say that what is the voltage here with this AC voltage. If we consider the maximum value of the AC voltage, because at any time your AC voltage going to be max at its maximum value. So this part of the circuit will have Vm into R upon total resistance in this particular branch. So this is going to be the maximum voltage applied here by this configuration. It should be always less than the maximum rating, maximum gate to cathode rating of the SCR. It will ensure the safe operation of your SCR, and this will give you the this relation which actually defines that what your R value is should be less than or equal to always VGM, that is the maximum gate to cathode voltage rating of the SCR into R1 upon maximum value of the AC source minus maximum value of the gate to cathode rating of the SCR. So this is all about the little bit theory part. Now we will try to simulate on the PSpice simulation. So quickly I'm going to that my capture CIS. Let's go to the capture CIS. Here we can create a new project. We have to select analog mixed AD project. So I'm going to give the name project underscore R firing. Okay, now I have already located my directly, so you can also uh, locate as per your desire that what is your going to be your directory. And I have also mentioned that how to locate these directory and other things, how to create new schematic and other things in the other part of video that you can find in my playlist. So let's start. Okay, now create a blank project. Okay, this will open your schematic window. Here in the very right side in the vertical menu, you will get the place part option so that you can place your parts. So to get the AC voltage source, we have to type here V sine. Okay, V sine source. This is going to be your AC source. We will take it one, and then we are going to take one thyristor, which is 2N1595. This one we can take, we can rotate by control R. We can place this thyristor over here. Okay, now we required some resistances and diode also. So for the diode, firstly let put some resistances. So resistance R analog, we can rotate it. Okay, this again we can place, and one more resistance we required for the load, one more resistance we required for the gate to cathode connection. Okay, uh, we can also relocate it as per our desire, because we have to place one diode also. The diode can be found out as a D1N4. So this is going to be, I'm going to take D1N4002. You can take any of the diode as per the ratings and configurations. Okay, you just adjust your SCR so that you can make a proper connection for this. Okay, now let's take the wire connection. Quickly connect your all the elements. Sorry, we can also move it by one place so that it will become easy to understand the connection. And now okay, here to here, this is going to be the gate to cathode connection. Okay, further we can rename the components. We need not to bother about the names. We can rename it as per our configuration. So now first of all, this is this is R1, R2 is okay. This can be the load, so you can name the load. Okay, also you can name it only R as per our circuit we have taken. Here we can give the AC supply. We also need to change the values of these resistances. So let's we can take 100 ohm. This R1 is also known as a stabilizing resistance. Here let's say it is a pot resistance or the variable resistance 1 kilo ohm. Further we can change these values. Let's say the gate to cathode resistance is 500 ohm. Okay, now let's 150 ohm resistor. Okay, you have to also connect a very important thing, ground, zero source. Otherwise if you do not connect this one, when you simulate without this, your project will say every terminal is floating. This actually provides the reference node to your project, so that it will connect properly. Now we will take V of value of AC source 0. We do not require any offset. Let's say it is a step down supply of a 24 volt from 232. Sorry, it is not a frequency. We have to give in 24 in voltage amplitude, and frequency can be 50 hertz normal your supply frequency. And how we can reduce it by using a transformer, step down transformer. V1 is the supply. We have given all the names over here. Okay, now where we have to observe our output across the load. So we can take this potential marker and we can place in between the potential marker as per the polarity, positive and then negative. Okay, it will give you the response across the load in which we are interested. Now after this we have to set that our new simulation profile in the PSpice menu. New simulation profile, let's say project R firing SP. You can give any name as per your desire. For better understanding, I used to give a SP notation so that we can understand it is our simulation profile. Now, when you do it, actually you will face this window. Let me go to that window. When you create new simulation profile, here you can give that how much run time is required. So we have given a 50 hertz supply, so we can say that let's 100 millisecond. Small m is millisecond. For steps are 0.0001. Okay, for the smooth operation apply it. Okay, now your new simulation profile is set. Now you can run your project by going into this PSpice menu, run option or F11. You just run it. Then a simulation window will be appear. Here the green color shows that your this voltage will be shown by the green color. Now go to our simulation window. Okay, now you can see that it is your rectified AC supply which is triggered at these moments. Let me set this one and make it more thicker so that you can able to observe it properly. Okay, let make it little uh, less thicker. Now, okay. So as per the resistance we have connected, we can see that at this particular angle, it is firing. Okay. Now, if we adjust our resistance, like in the schematic here, if we consider this is a variable resistance, if we change it, like for a timing, we put 2K, 2 kilo ohm. Okay. Now run it. Then you can see that now the triggering angle has increased bit from the previous case. Now again, if I want to change this one to the, let make it 4K, okay, double of the previous value. So run it. It takes few seconds. Now you can see that it is a good enough firing angle near about 45 or something degree. You can calculate that what is your firing angle by measuring these things. But let me go up to the 90 first. Then I want to show the result that what will happen beyond the 90. So let's say we make it 6 kilo ohm. I'll run it, and you can see that it is nearer to the 90 degree. Further we can also increase the value of resistance. As we are regulating these resistances, we are able to get the value. So here actually I have already done this simulation, so I know that around the 6.7 kilo ohm it will take a 90 degree operation of triggering. So I'm going to do that one. Let Now you can see that here clearly it is nearer to the 90 degree, or it is almost 90 degree. How you can identify? If you also add the trace of your supply voltage from here, go and search about the V1 plus and add it over here. Now you can see that this red one, let me make it thicker. Properties, go here and make it thick, and also you can select for this one and make it thick. Okay, now you can easily understand that at this particular value of the 6.7 kilo ohm of our pot resistance or the variable resistance, it is having a 90 degree. Should we try for the more than 90 degree? Let's try. Okay. Now I'm going to put some more value, like let's say 7 kilo ohm. Okay. Now let's say we run it, and we can see that the triggering is not working properly. Here we are, whatever we are getting, it is not a correct result. Here there is no triggering. That means your circuit is not able to trigger beyond the 90. Okay, from 0 to 90 degree it is possible, or practically it is from 2 degree to 90 degree, because 0 degree is also not possible because of gate to cathode threshold voltage of SCR. And you can also like refer your books to understand this particular concept. So I'll going back to the same value of a 90, which actually I placed for this one, 6.7 kilo ohm. Okay, now run this. So this is your waveform when it is getting triggered around 90 degree. Okay, now how to measure this one? For measuring this one, we can actually, it is a 50 hertz supply. What is your one alteration time period is 10 millisecond. So that means you can see that this is your red one is your AC supply. These many divisions are actually for the 10 milliseconds. So each here how many divisions? 1 2 3 4 5. That means each of 2 millisecond. So it is near about 2.4 or 2.5 millisecond is there. That means it is near to the 90 degree. Also you can use this particular toggle cursor option. You can go to this toggle cursor option, click here, and you can trace your cursor to this particular point. Okay, place it carefully here. Here in this particular menu, it will automatically get open when you select the toggle cursor option. A1, the first reading is showing the time x-axis, and the second reading is showing the y-axis. So 44.624 millisecond, because here we are actually occurring after the 40 millisecond. So it is near about 2.6 sorry, 4.624 millisecond. Okay, that means it is somewhere like this. Yeah, it is 4 point because each division of a 2 millisecond. So 2 millisecond, 2 millisecond, 4 and 4.624 millisecond. and further you can put the relationship alpha is equal to omega t, and if it is 4.624 milliseconds, so you can put in place of t 4.624, and omega can be 2 pi f, that is 100 pi, because your frequency is 50 hertz. So you will get the exact firing angle value for your any particular triggering instance. Like if I'll go below this for uh, 4K, if I'll run this, and if I'll get some results related to this lesser than 90 degree, okay, so we can easily understand that what is my firing angle. Take the toggle cursor and put it over here at the firing instant, okay, and it is 42.114. That means after the 40 millisecond it is 2.114 milliseconds. That means your t value is 2.114 millisecond into 100 pi is nothing but your alpha value that you can calculate. Okay, so this is all about your R firing circuit, and you can also like vary the different resistances over here. Okay, and to see the output report you can go to your simulation window, and here if you click here you find on the very left side vertical menu view simulation output file. If you click on here you will get your output report of your project also. So this is all about your R firing circuit, and I hope you understood it very well. So please subscribe the channel and press bell icon for the further uploads. Also keep watching the next uploads. Okay, thank you.